Hello and welcome. What we're going to be doing today is looking at how to look at circular motion questions and knowing how to approach them, because circular motion is so important. Because yes, it may be on paper one in its pure form, but it comes into near enough every aspect of second year paper two work. So what my focus is today is to first of all give you some tips on how to actually deal with circular motion. So my first tip is to know your terminology. So you actually know what is meant by the word speed, angular speed, and centripetal force. So I think the biggest difference is definitely knowing the difference between speed and angular speed. So speed is represented by the letter V. Okay, we use this as velocity as well, but speed is this thing here, V. And I've got a diagram here that I've put up. V is this, basically the instantaneous speed that the object is going. This can also be called, so the speed can also be called a lot of things. So we can call the instantaneous. That does not look instantaneous speed. So we call the instantaneous speed. It could also be called the tangential speed. Okay, and it's basically this part here. So if you had an object, so a pendulum, and that was moving in a circular motion, it is this speed here at that point in time. Okay, so if it was here, the actual object here, it's again this speed here, and it's at right angles to the thing. You can see it on here, it's at right angles to the actual object. Okay, it is measured in meters per second. It's measured in meters per second. Okay, and more importantly, it's also constant in magnitude in circular motion. So as this object goes round a circle, the actual speed, this is why I'm using the word speed and not velocity. It's actually moving around in a circle and its magnitude will stay the same. It's always constant. Okay, we use the letter V for velocity. That mainly because it's archaic, but we don't say circular velocity, we do say circular speed. And it's really important when you see the word speed or instantaneous speed or tangential speed, they mean V. Okay, they mean this bit here where it's going off at an angle. Now, angular speed is something slightly different, and it's only to do with circular circles. Okay, and this is represented by the letter omega. Okay, so this here is the basically the speed in regards to rotation. So what it is basically how much of an angle this thing sweeps out. Okay, so if we actually look at a circle here, so a circle has 360 degrees or 2 pi radians, and basically omega is measured in degrees per second or rads per second. So it's how much angle are you sweeping out every second. And what's actually really important is there are two formulae for omega, or the angular speed, and you have that omega is I'm just gonna put that again, 2 pi times by the frequency, or 2 pi divided by the time period. Okay, and actually if you look at it, this actually does make a bit of sense, because this here is your angle and this is your time. Okay, so another way that you can sometimes see omega written, this angular speed, is that it is the angle over time. And sometimes you do see that. So this angle could be in radians or it could be in degrees. We tend to use radians for circular motion because it makes a bit more sense when you talk about the times of revolutions. Okay, so just to remind you, this is the frequency. So this is how many that you're doing every second, so how many revolutions you do per second. So if you think about it, if you're doing 2 revolutions per second, every second you're going to be covering 4 pi's worth of that angle. Whereas if you were doing, it took you 2 seconds to do 1 revolution, you're only going to do, so 2 pi divided by 2, so that's your time period is 2 in this case. You're only really going to be covering half that circle, so you're going to be covering pi of that circle every second. So knowing the difference between these 2 words is really, really important, mainly because when you see a question, they may say, find the speed or find the angular speed. They will always call omega the angular speed, okay? The tangential speed might be called, or V may be called instantaneous speed, tangential speed, but they're always called omega. It's really important when you get a question that you're able to identify that's what they're looking for. They're looking for the letter, they're looking for the speed. So I know what formula I'm looking for. I know that I'm looking for the V. Oh no, okay, they're looking for that. I know what I'm looking for, omega. So it's really important that you recognize that terminology and can realize what they're talking about. If you have to, in a question, highlight, underline it, and then write what letter it is, V or omega, it will be really useful in the long run. Now, the last thing, the terminology you need to know is the centripetal force. There's a couple of things you need to know about that, okay? I'm just going to move the thing down here. There's a couple of things you need to know about centripetal force. Is it always acts to center of circle, so it always acts to the center of the circle. That it is a resultant force. It isn't a real force in its own right, okay? So by that, I mean it is what we call the resultant of the forces that are acting in the center of the circle. So what I mean by that, as an example, if I just go and grab this here and move it over. So if I had an imaginary circle like this, okay, and I've got the weight of an object pulling down and I've got the tension of the object pulling it up, the centripetal force equals the resultant of those 2 forces. So it's going to be the tension minus the mg, okay? Because I know that the centripetal is going to be going up, so I know resultant goes up because it goes to the center of the circle. Do apologize. Nope. Yep, maybe. Sorry, I do apologize. I might sneeze. So the resultant, I know the resultant, because it always goes the same. I know resultantly it must go up towards the center of the circle. So the resultant will be going up. And it is a resultant force. So it's a resultant of 2 real forces, which is the tension and the weight here. So the centripetal T equals mg. So you end up with F equals T minus mg. And what's actually really important is that you understand that this is a resultant force. And this kind of brings us on to the last point about centripetal force, is it is constant in a circle. Okay, in the circle. So at this position here, and by the way, it's constant in magnitude in the circle. What it means here is that at the top, at this section here, the magnitude of the centripetal force will be exactly the same, which means that the tension and the weight may be affected and changing. And this is kind of, we'll explain, well, when you sort of, for example, if you get a lanyard or a piece of string, you try to swing it in that horizontal circle, the rope is really tense at the bottom of the circle. And then when it's at the top, it's really, really slack. And that is because what's happening as it's going through the motion is the 2 main forces, the tension and the weight, are changing. but overall the resultant must be the same, or the magnitude of the resultant must be the same, and the tension and the weight change sort of their effect as it goes round in a circle. This is why in the Simpsons film, for example, you have the Wheel of Doom, and what Lisa's talking about is you basically, as she goes up, Homer keeps falling down, and that's because his reaction force is changing with the circle he's trying to make. And I will be explaining a little bit later, and I have done in my other video about circular motion, about this Wheel of Doom and how it works. Okay, so these are some kind of like the most important. Know your terminology, know what they mean, know that speed is the tangential thing. It is instantaneously alternate. They call it speed. It's the letter V. Know that angular speed is the letter omega. Okay, know that. Know that centripetal force is F, and it is the resultant force of the forces acting. Okay. So that's my first sort of like tip of how to deal with circular motion is, first of all, know these terms. My next tip is to find omega in a question no matter what. So if you are given a question, find omega and actually use it to develop your answers. Okay, it's a really, really important tool to use, is to literally just, if you can continue to find omega, you will basically help answer all your questions with this one. So let me just like pull up a question for you. So I'm just going to grab a question from a book for you, so you can actually see what I mean by always finding omega is so useful. So there it is. So let me just grab this question here. So this is a question from an example here. So what I mean by finding omega is finding, like we said before, knowing the donut is basically the angular speed which is going to be 2 pi f or 2 pi over t. And the reason I tell you to find this omega is because, one, it's really useful and it makes you realise you're actually dealing with circles, but all the other formula that rely on it. So for example, velocity, the speed, is going to be omega r. The acceleration is omega squared r. And from that, you can of course use F equals ma, which then equals m omega squared r, or you can of course use mv squared over r because you know what a is, and etc. So let's show you what I mean by knowing omega. So this is a question, an object with a mass of 0.15 has a circular path of radius of 0.42 and a steady rate of once every 5 seconds. So I know the time period is 5 seconds. I know the mass is 0.15 kilograms, and I know the radius is 0.42 meters. So the first thing I'm going to do, even before I even look at this question, is I'm going to find out what omega is. So finding omega is so useful. So I know it's 2 pi f or 2 pi over t. So I know that omega is going to be 2 pi over 5. So that's going to be 2 pi divided by 5. And that's going to be 1.26 rads per second. Okay, so this is what I do. I only looked at the rest of the question. I've just looked at the information. The first thing I try to find from my information is omega. So part A here, the speed. Again, this is back onto my terminology thing. The speed, which means I'm trying to find V. So I'm trying to find V equals omega r. So that's going to be, now I know omega, 1.26 times by 0.42. 0.53 meters per second there. So what I didn't even, like I said, I didn't even look at the question. The first thing I did was find omega. I didn't even look at the rest of the question, took the information, found omega. And that is one of the biggest hints I have for you, is to always try and find omega in your answer, okay? Because it is to be honest, one of the more powerful tools of circular motion. It also gets your mind going, cool, I'm looking for omega. Question B, okay, find the centripetal force of the object. So this is Newton's second law, F equals ma. So that is Newton's second law. Okay. So you're going to find the circular acceleration here. So A equals omega squared r. So it's going to be 1.26 squared times by 0.42. So times by 1.26, 0.67 meters per second squared. And then using F equals ma, you get, so 0.15 times by 0.67 is 0.099. So 0.1 newtons here. So there's one way you can do it. So this is actually using Newton's second law, because you know, if I go back up to centripetal force, it is the force pulling it to the center of the circle. Okay, and this Newton's second law applies for this one, but you can't, one of the things is that with the acceleration, you have to, because it's circular motion, you have to use that A. You cannot use change in V over change in T, okay? So we just put that over here. Do not use change in velocity over change in time, because that's linear motion, okay? This is circular motion. Always use the circular motion. This is why about finding omega first is really useful. You could, of course, use F equals mv squared over r. So that would have been 0.15 times by 0.53 squared over 0.42. That's perfectly acceptable. So 0.53 squared times by 0.15 divided by 0.42, again, is 0.1 newtons. Either is acceptable. You can also do, of course, F equals omega squared r too. That would have also got the same answer. So as you can see here, my second tip for working with circular motion is find omega no matter what. Try to. It's like one of the most important, most useful things in a question. And I've just given you an example there. My third tip for dealing with circular motion is to know what I actually do mean by the centripetal force, to know it's actually properly meant by centripetal force. And this all comes back to what I was saying before, but I'm going to give it a little bit more depth here, because there are many, many, many different kinds of circles that you can have. So basically, it is the force causing the acceleration. So I'm just going to remove all of that. Causing the acceleration inwards to the center of the circle. So it is what is causing, it is the resultant that's going to be causing the motion in the center of the circle. So for example, in, let's say I had a pendulum like this, and it was going around in a circle like this, here like that. Okay, the circle is here. Okay, so if I just put that here, so the centripetal force, the resultant force, is this one here. So F is the centripetal force. But where does it come from? That's the important thing. So where does it come from? And that's when realizing what's actually happening in circular motion. So if I actually draw a side-on picture, I've got this object here, I've got this tension here, and I've got this weight here of this ball that's going around in a circle, and this centripetal force here. This is a resultant force. It doesn't exist, really. I can't say, I am putting a centripetal force. No, I'm applying tension or weight or friction or something, and it's causing a centripetal force. It's a force caused by here. So, of course, this is going to be this force here. If I actually label the rest of my diagram, I know that T cos theta equals the centripetal force. This here, this is the real force. This is the forces, the real forces, the forces you're applying. So the force is applied. This is the resultant caused. So it's really important that you are very much aware that this idea that it's the force causing the acceleration into there, but it's the resultant. I should have put the resultant force caused there. That was me being a little bit. It's the resultant force causing the acceleration inwards to the center of the circle. So this is an example here with a nice lasso that's going around in sort of this circle here. But this is the resultant force. This is the force. This is the one that's causing the circular motion. And so if I actually look at the real forces, I know it's going to be T cos theta equals that. It actually is the force that's being caused. And once you know what F is, you can then use all the formula that you already know to find this. Okay. This can apply to any situation. Okay, so there are many situations that you can apply this to. So a really good example. So I'm just going to come down here. So there are three sort of main circles that we deal with. Cool. So the three sort of circles we deal with is the horizontal. Okay. So this is the one where you've got a force like this. Okay. A really good example, of course, is sort of orbits and things. So what you've got here is the Earth, and you've got this object is pulling it into the Earth here. So I'm just going to call this the force. That the force is actually the gravitational force. Okay, so in this case, the F is the gravitational force. So this is actually the force pulling it to Earth due to gravitation. And it's represented by this formula here, Gmm over R squared, where that is the mass being orbited. And this is the mass under circular motion. So in this case, this is quite unique that the only force is the centripetal force. So I know that Gmm over R squared equals mv squared over bit of a hang up on my thing today, mv squared over R. Okay, and it means that I can cancel the two m's here, and R can be cancelled, and I end up with v squared is gm over R. Okay. So what the horizontal circles are very much, there is literally one force acting, it's constant, nothing changes. They're probably the most simple circles that you can do. Okay. There's only literally, there is a force acting and it's constant. So it basically has a nice constant force on it. The next kind of circles are the vertical, and they are the ones that I showed you earlier. So what actually happens here is that you've got this object here. So it's like a Ferris wheel. ETC. And at different positions here, you have different kind of forces acting on it. So you've got your tension and you've got your weight, and you've got your tension and your weight. Now, there's always a reason I draw this like this. I always draw the tension as a reaction to the weight, because that's what tension is. Tension is a reaction due to a weight being put on it. And I'll call this position A and B. And you can watch my video on this. I do this in a bit more detail and a bit slower. So at A, the resultant force is going up. So the resultant force is up because remember, it's moving towards the center of the circle. Okay. And that's going to be the tension minus the weight. So the tension is actually going to be quite high down here. It's actually going to be the centripetal force plus the weight. And at B, the centripetal force is actually going down. So that's going to be minus F, and that's going to be tension minus the weight. So the tension here is going to be the weight minus the centripetal force. So what this actually implies is that as the object goes around this loop, is that the tension will continually change. So the forces are not constant, but the centripetal is. So the forces are not constant as they're going around, they're changing. You can see that if you swing a lanyard around that, you've got really high tension at the bottom, and at the top it sort of compresses. And that's because the tension in that rope is changing as it goes round that loop. Okay, so the first one here is that you have a horizontal circuit, it's constant, nothing's changing about the situation, it's just centripetal force equals the force that's going inwards, and it's nice and constant and nothing changes. Whereas in a vertical circle, things change consistently as you move around in this circle. The third circle, of course, is at the angle. Okay, and that is that components of forces attribute to the centripetal. And again, I've done a video on this. A really good example here is if I had a car, here's a box here. I've got my weight downwards, my mg there, and I have my reaction here, force there. So it's moving around in a circle like this. So that is where F should be. There's theta. So I know that R cos theta is my F there. Okay, so it's components of forces. So at the angle, components of forces attributing actually to the centripetal force. They're the thing causing the centripetal force. Okay, so that is sort of understanding what centripetal force is, and that's kind of will lead me to my last part here. So it says here, know exactly what is meant by centripetal force. It is the resultant force causing the acceleration into the center of the circle. Okay, so it's always looking at what happens. And this is actually where it brings to my last point, is what forces are causing that force. And that's exactly what I was covering here when I always write this down. So I always go, the horizontal force, I know the force that's causing the circular motion is the gravitational force. And that equation for that force is gmm over r squared. And then I make that equal. Okay, exactly the same with the vertical circles. I go, the resultant force is this, and this is what it is all about. These are the forces causing it. Okay, so these are the forces causing. Oops. So these are causing the force, and then I relate that to the thing. It's exactly the same. So I'll just give you a quick example here. This is exactly the same what you would do in linear motion. Okay, So just to make you aware, in linear motion, if I had a box on a slope, for example, okay, and I had the friction here, and I had the weight downwards, and I had the reaction there. Let's at this angle. Okay, so if I wanted to find the acceleration down the slope, okay, so if I wanted to find the acceleration down the slope, I'd find what forces are down there. So what are the forces down the slope? Well, that's going to be mg sine theta. Okay, so that's going to be pulling me down the slope minus the friction. So the resultant down the slope, this is a linear example, is mg sine theta minus the friction. And then you apply your F equals ma. So you know that the resultant force would be ma, and you then would go mg, you know the resultant force down the slope is mg sine theta minus the friction, and then you would solve it. The exact same thing goes for circular. So let me give you an example here for circular motion. So let's have a object here, tension, mg, and let's say that this is 1 meter, the center of the circle. So this thing is orbiting, sort of like swinging it around, okay? And let's say that this is 30 degrees and m is 1 kilo, okay? And they ask me to find the speed of the pendulum. Okay. So I'm trying to find the speed of the pendulum. Now, I would normally say find omega first, but you haven't got enough information for that. So what I'm actually trying to do here is you're trying to realize what is causing the circular motion in the first place. So the force is causing circular motion. If you look at this, so this is where F should be, okay? This is where this is the resultant force. The only force that's going to help with that is going to be T cos 30, okay? That is the force called, this is F, okay? So let's actually find T. I know it is only moving in a circle. So it is in equilibrium up and down. Oops, see if I go down a bit. So if I actually draw a diagram, I've got T here, and I've got G here, because it's 1 times G. So I know that T sine 30 equals G. This is in the y-axis. And I know that T cos 30 equals the centripetal in the x-axis. Because this is the first thing I did. I identified what was causing the circular motion, the forces that were causing it, and it was T cos 30. Okay, so I'm finding the forces that cause the circular motion. So let's find out what T equals. So T equals, so T sine 30 equals 9.81. So 9.81 divided by sine 30, and I get 19.62. Which means that the centripetal force is going to be equal answer times by cos 30. So 16.99, 17 newtons. And now, because I know the centripetal force, I know the value of F, I can then use F equals mv squared over r. Okay, so I know 1 times 17 divided by 1, 17 squared. Oops. That was my fault. Sorry about this. Joy of playing with this. So here, did that a bit wrong there. So I know that 17 equals 1 times v squared over 1. So v equals square root of 17, about 4.1. Okay. So I knew, again, this goes back to the terminology and all that. I knew I was looking for v, okay, of the pendulum. And the first thing I did was found the forces causing the circular motion. So I actually looked at the diagram, went, what is actually causing the actual thing? What is basically what components or forces are acting in the same line as the centripetal. So I was always I'm actually looking what forces or components are acting where the centripetal force is acting. So what I tend to do is draw a lovely dotted line. I write an F. Okay, so this here is my centripetal force. I can go what forces are acting in that direction. Okay, and the same goes if I go all the way back up here to my Ferris wheel. Okay, I know that here my F is going to go downwards there. And I know that here my F is going to go upwards. So I know where my centripetal force is going and I know what forces are acting where, okay? So just to recap, my four tips to circular motion are as follows, okay? Firstly, know your terminology. Know what speed, angular speed, and centripetal force really mean. Number 2, when you can, try and find omega. If you have information about its orbital motion, its time period, whatever, find omega first. Even before trying to answer the question, try to find omega from the information you've been given to see if you can do it. So the kind of things you're looking out for if you need omega are frequency or time period. Okay, the rest of it you don't to apply. Just be very, very aware that sometimes they may sneak it and say, what's the orbital, what's something about Earth? Okay, remember you do know the orbital time for a day on Earth is 24 hours or 86,400 seconds. Okay. My second one is know exactly what I mean by centripetal force. Know it is the resultant force causing the acceleration towards the center of the circle. Know that the centripetal force is not a real force. It is a resultant force that is caused by either sometimes the case of just one force acting towards the center of the circle. Sometimes it is a resultant between two forces, or sometimes it's components. Okay. And which leads us to the last one, which is knowing what that causing the force, identifying what force, where the centripetal force is, and having a look at what forces could contribute to that. So I did a nice linear example. This is not circular motion. This is just F equals ma and stuff we do at first year. I wanted to know the acceleration down the slope. So I looked at all the forces that were acting down the slope. And then I found the resultant, and then I used F equals ma. Exactly the same is for circular motion. That I look at what forces are causing the circular motion, and then I try to solve it. And once I know what the value of the force is causing that, either by using components or whatever, I can then use mv squared over r. So much like a linear example where you would find the resultant force first and then find the acceleration using F equals ma, what you do is you try to find the resultant force first, F, by using components and stuff like that, and then use circular motion. Okay? So that there are my sort of top tips of how to deal with circular motion questions. I'm going to use these again when I walk through some more exam questions. but hopefully these will help you in the long run. So there we go. That is some of my top tips for how to deal with circular motion.